We stand at a scientific precipice of sorts. It seems like the more we learn about the universe, the more questions it presents to us. This reflects a new era of science, a kind of hyperfocus, where we can study the universe at unprecedented levels, yet still have to grapple with the new questions that arise as a result of that precision. To paraphrase a famous person from the past, we are faced with the known and the unknown knowns. The question that comes after that is how to communicate these mysteries to the public at large. My guest today is part of this new paradigm of science communication. She is not only a research fellow at Oxford, but hosts a channel here on YouTube, and has now written a new book about the unknowns of our universe.
Welcome to Event Horizon with John Michael Godlier. In today's episode, John is joined by Dr. Becky Smethurst. Dr. Becky is an astrophysicist and research fellow at the University of Oxford. Her YouTube channel, Dr. Becky, is where she explains unsolved mysteries, weird objects found in space, and general space news each week. She has also authored a new book titled Space: 10 Things You Should Know 14 Billion Years for People Short on Time.
Welcome everyone to Event Horizon with me, John Michael Godlier. If you enjoy what you hear, fall into the Event Horizon, hit the like button, and become an active subscriber by ringing the bell. Dr. Becky Smethurst, welcome to the program.
Thank you. I'm very excited to be here.
It's great to have you, Doctor. I've watched a bunch of your videos on YouTube, and you just have a certain way of explaining certain things and picking subjects that nobody else talks about. I watched your video on the Hoax object, which I'd always seen the pictures of this thing, and I'm like, how did that happen?
Yeah, well, those are the things that I love, though. The cool, weird stuff, and I use weird there in like a good sense. Like it's weird is good. That we still like have no idea about. Like we'd like to think that we have some idea, but in reality, we're still sort of just fumbling in the dark to try and explain it because these things have been formed over billions of years and by a countable number of processes. So trying to wrap your head around that is difficult. And I think people love that side of science.
Oh, it's the best side, the unknown, and it keeps coming at us very rapidly lately. I don't think I've ever seen a year like 2019 where just story after story of interesting mysteries just comes flying at you. And when you have to do YouTube channels like we do, it becomes triage trying to cover it all.
Yeah, exactly. People are like, why haven't you talked about this? I'm like, because I wanted to talk about the other cool thing that happened.
I know it happens to me too. And you end up just going and doing back videos to try and cover something from last year, that you just really wanted to cover, but didn't have the time. There's just too much.
Yeah, exactly.
We'll never run out of subject matter on YouTube.
Exactly. But the cool thing is, though, if you do leave it a year, you then have that sort of perspective that when like the first videos came out talking about it or explaining it, they didn't have that perspective of a years later of more results coming out and more study being done that allows you to actually gain a better appreciation for something. So I think maybe we should do that more on YouTube, is just take a minute and wait a little bit.
Take a minute, take stock.
Yeah, exactly.
Yeah.
So I did that when the Event Horizon telescope image of the black hole in Messier 87 came out earlier this year. Do you remember it? It was that kind of like
yes.
orange donut thing? Yeah. So I was going to do a video that day. And I was just like, whoa, hold your horses. Like, let's just wait a week to see after the week's gone by, like what else is published on this. Because it's amazing. The astronomy community is so fast. All our papers get posted to something called the archive, AstroPH.
Yes.
Yeah, which is great because it means that they're all open access, so anyone could read them. And people can get posts up there about brand new results, a couple of days, short papers just reflecting on something or saying, oh, now we've done this is possible. And so I think that's really nice to be able to wait and then read those and see what people are all saying, on on the archive, but also like on Twitter and everything as well, just to get those immediate reactions from people working in the field, and then sort of report back and say, this is what's going on. I think that's really cool.
I do too. And I mean, I look at the archive every day, or at least every weekday, and it's really an amazing repository of knowledge and ideas. I don't know of anything quite like it because it's just free and open access for anybody.
Yeah, and it's really good that the journals that we then actually publish to and, like pay to publish to don't mind the fact that we can then just put it on archive. There are some, like I don't think Nature really likes it, but the rest of them are just like, yeah, check it on archive, make it free and open access. And I think that's the way that like science publishing should go. Like it made sense in 50 years ago when you were actually paying for actual paper to be printed. But when it's just a PDF online, people have really started questioning, is this the right model that science should be going forward with? Paying for publications that only certain people who've got the subscription can see?
Right.
It should definitely be more open access. And I think astronomy is really leading that vision of this open access future of science.
Yeah, it really is. And AstroPH is just the premier way to do it. Now, to switch gears a little bit, what drew you to become an astrophysicist?
So, I mean, I was just one of those kids, right? Everybody knows what I'm talking about when I say one of those kids that just wanted telescopes for Christmas and got bought books on space by every single auntie and uncle that didn't know what to buy me. And I just devoured them. I absolutely loved them. And I just could regurgitate facts to passing people like, did you know? Like a really annoying child. And so as I got older and went through school, I realized that all of a sudden we then started to learn about astronomy in science. And I was like, oh, this is a thing that you can do. The problem was that I'd always thought that everything was known. Like I was reading these books and they were just presenting all of these facts as if they were known and they'd always been known, which is great for a book that is trying to document that. But when you then are growing up and you think, well, I can't do that because, we know everything already. There's nothing more to know. And as I got older, I realized actually we know nothing. And then realized that you could do that as a career. It was a no-brainer for me to go to university and study astrophysics. Why wouldn't I pick my favorite subject that I've always had a passion for? And everyone in my life told me that was a great thing to do because, if you do a subject you love, it probably leads to a job you love, whatever that might be. And I can attest to the fact that I absolutely love my job because it's awesome.
Absolutely. Even though I work in the peripherals of it, just science popularization, it's basically I'm the amateur astronomer talking on YouTube about this stuff. And I look back and I'm like, God, I love doing this. And I can't believe that I actually make my living at it.
Yeah.
I
sometimes have to pinch myself.
Yeah, sometimes you have to. Now, was there a moment when you were a kid looking through a telescope? Did you see any particular object that was like, that's it, I have to go into this career? Was there just one moment where you just knew you were in love with astronomy?
I do remember one thing that I don't know whether it was maybe fall in love with astronomy, but it really annoyed me because I just remember being somewhere, I don't even remember where it was, but we were somewhere where the night sky was very dark. And we were looking at the night sky and we were looking at the constellation of Orion. Everyone's probably familiar with Orion's belt, the 3 stars in a row, but Orion, the constellation, is a lot bigger. It's supposed to represent like a hunter, with sort of a shape of a man and then like a bow and arrow and everything. And essentially the top shoulder of Orion is a star called Betelgeuse. And I asked my mom and dad, turned to them and said, why is that star red? And they were like, we don't know. And that really frustrated me as a kid. I'm like, why don't you know? Surely you should know something like that. You've been looking at the sky for so many decades. You should have noticed and you should have gone to find out. I was a very annoying child. And so I then immediately was like, I have to find out why the star is red, which I was sort of maybe like 9 or 10 at this time. So it was really the early days of dial-up internet. So I don't think we had it at home. So it was really like a, Mum, when can we go to the library next so I can go and find out why the star is red? And I remember finally finding it in a book. I'm just, my mind being blown that Betelgeuse is red because it's what we call a red giant star. It's at the end of its life. It's kind of run out of hydrogen. It started to swell up to this huge size. And it's just incredible. I think the size comparison is if the sun was the size of a tennis ball, then Betelgeuse would be the size of the London Eye, which is the Ferris wheel in London. And it just blows my mind every time I think about it still.
In the particular case of Betelgeuse, it only gets better because as you look at artist depictions of it, it's this gigantic roiling mass of hot gas that could explode, as I recall, at any time, right?
Oh, yeah, anytime. It's one of those like astronomy things where it could be any time, but any time means like in the next 100,000 years or something. But it literally could be tomorrow. And or
it could have been yesterday.
Well, yeah, we wouldn't know about it.
It already happened.
Exactly.
When that star goes supernova, that's gonna light things up around here, right? I mean, that's gonna be an amazing sight.
Oh yeah, like that's gonna be visible during the daytime sky if that goes supernova. When have we ever had something like that? Where it's like, there's the sun. Oh, and look, there's Betelgeuse. In the daytime sky. That's gonna be really strange. We'll be able to say that, like, on the beach, we'll be starbathing.
Starbathing.
Because it's not just sunbathing, because all of a sudden you can see two. So you're starbathing, right?
I've always regretted it because when I was really first getting into astronomy as a teenager, all the talk was about the one visible supernova that everybody could see, and it was in the southern hemisphere. And I couldn't see it.
Yeah, the southern hemisphere stuff frustrates me so much. I made a video on this last month because I've always wanted to be able to see the center of the Milky Way from where I live. The southern hemisphere has the best view of the night sky, in my opinion, because you can see the center of the Milky Way, you can see the Magellanic Clouds. All the interesting stuff seems to happen in the southern hemisphere, like the supernova that was visible, when you were a kid. And it just frustrates me so much. And not a lot of people realize, like, why we don't get the same view as the southern hemisphere is because if you picture, the Earth going around the sun and the sun going around the Milky Way, you imagine all of that sort of lined up in a single plane. But in reality, actually, the plane that the Earth goes around the sun is tilted by about 60 degrees to the plane the sun goes around the Milky Way. And so the southern hemisphere always points towards the center of the Milky Way, and the northern hemisphere always points outwards, which is kind of annoying.
It is an interesting thing. And then when you see the southern sky for the first time, even though you're intimately familiar with astronomy, you look up and you don't recognize anything.
No, and my favorite thing to do when I don't recognize anything, which is I do a lot. I went to Australia a couple years back for my PhD, and I just lay there and started making up constellations because why not, right? That's what people did millennia ago, is started making up constellations if you don't recognize anything. I tend to find a lot of stegosauruses, I'm not gonna lie, because I'm just like, oh look, there's lots of triangles that I can make. So dinosaurs in the sky is probably one of my favorite things to try and look for.
One wonders how the dinosaurs would have felt about that, though.
I wonder if they had their own dinosaur-shaped constellations, if they ever really progressed to that level of intelligence.
True.
We'll never
Orion
know.
was it was a velociraptor to some sort of a sauropod dinosaur.
Yeah.
Now you have a brand new book out, Space: 10 Things You Should Know, 14 Billion Years for People Short on Time. Now that's a really interesting subtitle.
Yeah.
Tell us a little bit about writing this book.
It's my favorite subtitle, 14 billion years for people short on time. I applaud my publishers for that one. So this book is 10 short essays, chapters, whatever you want to call them, on the 10 biggest things that I think you should know about in astronomy right now. So the things that people in the field are still thinking about. And it essentially covers what our best understanding of them are right now. And I say in the book, that can change. That's not going to be set in stone like the facts that I read as a kid. This is subject to the scientific process of gaining more evidence and revising hypotheses and having new accepted theories. We tend to sort of scoff at the fact that people never thought the atom could be split. Like, how could they ever think that kind of thing? But, maybe people scoff at our theory of dark matter in 50 years or so. Who knows? And so I try to emphasize that in the book, that these are things you should know, definitely. And if you're at a dinner party and you just want to be like, oh yeah, did you know this? Or someone brings up like dark matter, you can totally respond because you read this like nice, concise little chapter that I wrote. And then at the end of the book, I really push that idea that there's so much that we don't know compared to what we do know. And I talk about this idea of unknown unknowns. Do you know of this sort of paradigm? Yeah, you have the known knowns, the things that we know. You have the known unknowns, the things we know that we don't know. So things like, we don't know what dark matter is made of, for example. And then you have the unknown unknowns, the things that we don't know that we don't know. Fair enough. We have no idea what they are. We'll live in ignorance until we know them. And then you have the unknown knowns. So things that we don't know that we know. So, maybe there's a huge database somewhere with this amazing scientific result buried in it that no one's managed to find yet. We have the data to know about it, but we don't know about it yet.
It's interesting you say that, because the last guest I had, that the episode was out yesterday, actually was going through old photographic surveys to find other examples of KIC 8462852 type stars, tabby stars, Voyagian stars. And he actually found 21 of them in old surveys.
Yeah, exactly. It's crazy, isn't it? The idea that we could have known about this so much sooner, but we don't, and it's only with that hindsight that you can look back and find those things. And it just fascinates me. If I'm really struggling to get to sleep at night and I start getting onto that topic, well, I'm not getting to sleep at all that day, because you can just spiral out of control thinking about all the things that we could be missing. This key piece of information that's been sat in front of our faces for so long that we haven't figured out. Or if we could just link two things that seem like completely opposite ends of the spectrum on scientific results, and yet they would help solve each other in some way. It really, really gets your mind going. Let's put it that way.
It gets hard to envision, though, because you run into a really problem. You get into, where do you start looking for something that you don't know about? So you could miss something simply because you don't know how to look for it, because you don't really know what it was, and it wasn't what you were looking for. So if you do a survey looking for, variable stars or something like that, you may miss certain other things that just simply because you're not prepared to look for that. So there could be all kinds of things in these old sky surveys that we just don't know about yet.
Well, exactly. And the other thing about those whole sky surveys especially is that people write algorithms to essentially route through their data for them and get rid of the stuff they don't want. So they could do a survey for variable stars and throw out everything that's not variable. Well, what if they threw out something, the computer threw out something that it didn't recognize that was actually like a major result? And I think that's where we really struggle in science and astronomy, especially with this idea of big data. That's like a buzzword at the minute, big data, right? Everyone wants big data to go through and data scientists to try and sort stuff out. But I think it means that a lot of needles tend to go undiscovered in the haystacks of big data.
Interesting. Very interesting. We have to take a break. Everybody check out Dr. Becky's new book, Space, 10 Things You Should Know, 14 Billion Years for People Short on Time. Available worldwide right now and will be available in the US and Canada shortly. And we're back. Now, Doctor, one of your interests research-wise is black holes.
Yes, they are where my heart truly lies. And I say that very much so in the book, saying if it feels a little biased, this is probably why.
Now, what draws you? Is it just that black holes, I guess, are the ultimate mystery, right?
A little bit.
As far as this...
Yeah, as far as astronomy goes, I think the biggest ones are obviously dark matter, dark energy, but also black holes. We think we understand them and we've come up with this way of describing them. But at the end of the day, we're never going to observe a black hole because you can't. By definition, the light can't escape because the escape velocity is greater than the speed of light. So you're never going to get any information from out of the black hole. So all you have to go on is everything that's going on around it. Stars orbiting the black hole, or gas orbiting it, or gas falling in to be what we say accreted by the black hole, actually sort of taken in and then added to the black hole's mass. And so I think it's really, really fascinating. And what I think is incredible is that, and I'm going to say something that might throw people here, but the black hole is so small. And that is probably a strange thing for me to say because everyone's like, no, black holes are huge, right? They're incredibly heavy and they're very, very big. But they're small in comparison to the galaxies that we find them in. And so a galaxy can be hundreds of thousands of light years wide, and the black hole is small as in the solar system, not even a light year wide in some cases. And so what fascinates me is that something that is that small can actually have a huge impact on the entire galaxy. And so my research is actually trying to figure out, well, if you feed the black hole and you add to its mass, then how does that affect the galaxy? And if you feed the black hole too much so that it actually can't accrete all that material at once, because it reaches this sort of like limiting pressure of how much you can sort of add to the surrounding area, it actually throws out a load of that material before it even makes it to the black hole. And it gets thrown out speed of light, huge energetic jets. And we think those can actually impact the galaxy, like stop the entire galaxy from forming more stars, because you end up putting all that energy back into the gas that you're going to use to make more stars, and it heats it up and stops it collapsing under gravity. And that just fascinates me, that idea that something so tiny can have such a huge effect on one of the biggest structures in the universe.
It's interesting that the size of the black hole being so small yet so powerful sort of parallels how gravity is. Gravity is this incredibly weak force, but then you have a black hole where it suddenly is an overpowering force. And it sort of parallels that these sometimes small things can be very, very important.
Yeah.
In fact, in gravity's case, we couldn't even have a universe as it is.
Well, exactly, yeah. Because, we always talk about in astro how gravity is so much weaker than the other forces. So you have the strong and weak force, which is what governs sort of the inside of atoms, and they're incredibly strong, despite the name weak. And then you obviously have electromagnetism as well, which we're very familiar with, but it's much stronger than gravity. It's something like 11 times stronger. And that's very evident when you think about the fact that, you can grab a tiny magnet, right, and hold something up above the surface of the Earth with this magnet, which, if you stop to think about that, that's amazing. The entire Earth is pulling down on whatever you're holding up, say your keys, and yet you're resisting it with a tiny magnet. And I think that really puts into perspective how much stronger electromagnetism is than gravity. And yet at the same time, gravity's still been able to take us from a superparticles to the huge structures we see today, just through this, like you say, like snowball effect of eventually getting towards these massive, biggest energy type things.
Now, when you go to the atomic scale, gravity almost disappears. It's so weak at that level. Do you think we need a quantum theory of gravity? Do you think that's where the answer to understanding gravity lies? Because I know Einstein spent the last decades of his career trying to come up with a quantum theory of gravity. Do you think that's necessary? Do you think that's the direction we should go? Or is gravity something we may never completely understand?
I think it's definitely something we should explore. Like, I don't think we should just rule it out saying, no, we don't need that, because you never know what new nuances you could come up with or new understanding. It is strange to me that we have Einstein's theory of general relativity, which is our best theory of gravity, and we can test it, at the biggest masses, at the highest energies. The Event Horizon Telescope image we were talking about before, that also was in agreement with Einstein's theory of general relativity. So we've been able to test it in the highest masses energy regions. And yet at the smallest masses, we break down, which is incredible to me if you think about how he's saying, like, it's obviously so different on different scales. But I think trying to find that theory of quantum gravity would be incredibly useful. Where it would be applicable, I don't know. I don't know if it'd be generalizable across the entire universe and across all masses. Who knows? But we need something, I think. And even if it turns out to be negligible at those kind of masses and scales, like, fine. But at least we'll have some more understanding and we'll be able to rule it out as a possibility to explain it. I think the more important thing is coming up with this grand unified theory of all the forces and everything. I think that would be really cool. But I'll leave that to other people. That's not me.
Now, with black holes and gravity, there's another component here, time and time dilation. And gravity, being apparently an acceleration, just like any acceleration, is able to affect the flow of time locally. Now, how is it doing that? How does that relate to, why does gravity affect time?
Yeah, it's a really strange one. It's all to do with the speed that you're traveling at. So obviously this is Einstein's theory of special relativity, different from his theory of general relativity. And this is how, an observer's frame of reference, he referred it to. So essentially, like, how you observe things changes with what speed you're going at. And so around a black hole, your speed obviously very much changes. It can be very affected by the black hole. And so you get all these strange effects where time passes more slowly for you. I kind of thinking of it as sort of like moving through thick treacle, but you feel like you're sprinting in a way, is how I tend to sort of visualize it and rationalize it in my head. So it's a really odd thing, and we get this thing what we call a gravitational redshift as well. So redshift is when we often refer to it as the universe, as it expands the universe, you can stretch light to longer wavelengths, and so they become redder, because red color light is a lot longer wavelength than blue colored light. But that can actually happen around a black hole as well, because the light has physically been sort of slowed down by the effect of gravity around the black hole. So there's so many different effects that have to be taken into account. And so, we often get asked, well, what would happen if you fell into a black hole? And the sort of boring answer is that an observer, if they were watching you fall into the black hole, would never actually see you reach there. They would essentially see you just get slower and slower and slow down until you hit the event horizon, because the light getting to us would just be slowed all the time, and so would eventually never reach us beyond the event horizon. And so to you would still feel like you'd fallen in. So it's a really odd one to consider. But I mean, if you were to fall into a black hole, you would get spaghettified, which is my favorite word in all of science, spaghettification. The gravity would be so much stronger at your feet than at your head if you were falling feet first into a black hole, that you'd get stretched out like spaghetti. And I want to try and work that word into a paper one day, and then I think I'll be done for my scientific career.
It could even be a good book title, Spaghettification and You.
Yeah. Yo, spaghettification and You. I really like that.
And falling into a black hole.
Yeah, that's awesome. Yeah.
Now, let me try to visualize this. Okay, so we're observers in orbit around the black hole. Mm-hmm. And some astronaut that we've sent out accidentally made a mistake and is falling into the black hole. Yeah. So we would see their image redshift and basically fade out, right?
Well, yeah. So say the unfortunate astronaut that's fallen in has got a torch with them, and they're sending a pulse of light from that torch. They're turning it on and off every minute to them, right? Uh-huh. To us, as they fell in, that they would come later and later, those pulses, as the light was affected by the gravity around the black hole. And so eventually, when the unfortunate astronaut hit the event horizon and crossed it, we would then be waiting for eternity for the next light pulse to come, as they get further and further and further apart due to this effect of gravity on the light coming to us from the black hole, as it's essentially slowed down.
In the frame of reference of the astronaut, however, mm-hmm. they, up until spaghettification, which presumably would kill them instantly, but but up until that point, let's say we have a Superman that can actually survive. He's made out of some kind of exotic matter that isn't.
Sure.
And he actually...
Maybe it's Thor, because Thor didn't get killed by a neutron star, did he?
True. So okay, we'll go with that.
Black hole.
What happens when you actually hit the event horizon? What to the person that's actually there? What would they see?
Nothing. That's the thing. It's not like a demarcation line. There's nothing there essentially that they would see. They would still be able to see out, and they wouldn't even be able to tell that they crossed the event horizon.
So would they, as they cross it though, would they begin to see what's at the center of the black hole, the singularity? Would they see that?
That's what we don't know. That is one of the things we still don't know. And it's a difficult one, because you kind of feel like, all this light that's perhaps fallen into the black hole, is it trapped there now? Like, if they cross the event horizon, are they all of a sudden going to see all of that energy and light, compressed in there? We don't know, do we? Because it's a really interesting one, like trying to think of what it would look like. We have no idea what the matter inside a black hole is even like. Neutron stars, which are sort of the most densely packed version of matter that we know. These are essentially, you forced all your electrons and protons to come together, and all you've got left is neutrons, and they're arrayed in a crystal as tightly packed, like no space between the neutrons, right?
Yes.
And that's a neutron star. A neutron star, if you add too much mass to it, can collapse and become a black hole. It can reach that point where the escape velocity is greater than the speed of light for how much mass you've got in that small space. At that point, we don't know what form the matter takes in there. People hear black hole and they think of it as a hole, but it's not. It's just so much matter in one space. It's actually almost the opposite of a hole. We should probably call them like black mountains in a way. And so it's weird to think, well, if you cross the event horizon, would you would you just see something that looked like this sort of inert lump of matter? Or is it turned into like pure energy? By Einstein's, E equals mc squared, energy and mass are equivalent. We don't know. And I think it's one of those questions that we might never be able to answer. And I guess we kind of have to be okay with that.
Now, it's interesting. Some people envision it, I think a Kerr black hole is what it's called, where it's sort of a ring of material, maybe?
Yes. So this is one of these weird mathematically driven theories. So obviously there's a lot of people trying to study black holes, whether they come from an observational perspective like I do, whether they come from a simulation perspective, so putting laws of physics into a computer and seeing what that can tell us, or a completely theoretical, mathematically driven perspective. For example, that's what sort of Stephen Hawking would do. He would come from it from a very theoretical perspective. And so Kerr was also someone who did this and tried to study it and tried to come up with the mathematical formulation to describe a black hole, which is essentially, if you think about Einstein's theory of general relativity and mass curving space-time, and what you end up with when you've got a black hole is this singularity, as you pointed out, which is essentially a mathematical word, meaning you need to divide by zero at some point, which people who are keen mathematicians or number file fans will know that dividing by zero, not a good idea, not a thing that we can really do. It's not something that's really mathematically defined. And so if you follow that mathematics through of well, how can you describe it instead? You sometimes get these mathematical theories that make perfect mathematical sense. And then when you translate them into what they physically mean, you end up with this thing where okay, well, it's a ring. A black hole is a ring, which it very well could be. There's nothing to say that it couldn't. And if the maths makes sense, then maybe we should follow that because it's sort of led us in the right direction before. But it's one of those things that I think is an odd thing to get your head around because, we don't really see many ringed structures, do we? So, but it could be that it's just, so exotic and so energetic that is something that we have to consider as well.
Now, one thing that interests me is the detection of gravitational waves. And do you see a time where studying the interiors of black holes might become possible through studying gravitational waves through black hole mergers? Do you think that's a possible way in?
It could be, yeah. We get a lot of information from gravitational waves. At the minute, it's limited to comparing what I'm going to use see in the loosest sense of the word here, but what we see when we detect gravitational waves and what our models can tell us. So essentially what they do is they'll say, okay, in our best understanding of gravity and black holes, if two black holes of these masses and everything, merged, what pattern would we see in the gravitational waves? And so then when they detect some gravitational waves, they'll compare it with a ream of models in order to be able to say, okay, this was, two black holes, one 10 times the mass of the sun and one 30 times the mass of the sun that have merged together. And so I think our understanding of gravitational waves at the minute is actually limited to our models and how good our models are and how good that understanding is, which is another reason that the theoretical side of things will then push the understanding from the observational side as well. And maybe one day we will be able to glean some information about the interior of the event horizon from these gravitational waves if someone comes up with a way of, putting that into the models, perhaps. Or perhaps maybe we'll just discover some gravitational wave pattern so exotic that it doesn't fit with any of our models, and then that will drive, the theoretical understanding forward as they try and match what we've seen. But I think it's such an amazing discovery and tool, the LIGO, Virgo, and soon the LISA experiment that they're going to put into space. It really did. I never thought I'd live through a lifetime where we'd be seeing into space with something other than light. I think it's really, really incredible.
It is, and watching it unfold has been utterly amazing. Now, is it a safe thing to say that, a black hole, and I think it was Stephen Hawking that mentioned this, that it's just ambiguous. Past that event horizon, it's ambiguous and really no longer part of our universe.
Yeah, ambiguous is a good word.
Do you think that's really the case, that it's really could ultimately be unstudyable because it's just no longer part of all of this?
Yeah, I could. It makes me feel sad to say that, but yeah, it could be that it is this, no longer part of our universe, but perhaps the laws of our universe break down within the event horizon as well. Perhaps we'll never come up with a way to describe it, because, perhaps it's linking multiverses or something, these big theoretical ideas that's being studied at the minute where, perhaps we're expanding into another universe and eventually that universe will start expanding and we'll start contracting, and there's, infinite number of multiverses all connected by black holes and gravity's leaking between them, which is why it's so much weaker. Big ideas that are seriously being considered by theoreticians in universities across the world. But that is the problem with them being ambiguous and with them being perhaps outside our universe, is that we will never know because we'll probably never be able to study them.
But it brings up an interesting question, because there's also ideas like white holes, where, the other side of the black hole is this explosion of matter, which looks suspiciously like a Big Bang. Do you think there's any validity to the idea that we may actually be living inside of a black hole or be the remnant of one?
Yeah, I think that's a really interesting idea. Again, it's one that's really based in theory alone. I think with the number of black holes in our universe, we have a supermassive black hole at the center of every galaxy. There's stellar mass black holes that are like 1 to 2 times the mass of the sun compared to sort of the million and billion in the center of galaxies, that are just roving through our galaxy. We think there's a number of hundreds of thousands to a million of just normal black holes in our galaxy and in other galaxies. And when I think about that and I think about the number of black holes, I kind of think, well, if white holes were the other side of a black hole, surely we should have seen some, especially if it's just this great big whopping giant bright thing spitting out pure energy or matter. I think we should have seen some. Of course, there is the argument that, well, maybe they're going into, like we said, another universe and creating other universes as they do so. Perhaps they are, and perhaps our universe is inside it. But it's one of those things that I think until people come up with observationally testable ideas about that theory, so like things that you could actually question and go away and observe, we'll never be able to know whether that theory has any validity, I don't think.
And on that, we have to take another break. I'm joined today by Dr. Becky, author of Space, 10 Things You Should Know, 14 Billion Years for People Short on Time, which I really, really like that subtitle. I'm an author as well, and I know a good subtitle when I see one. We'll be back in a moment. And we're back with Dr. Becky Smethurst. Now, Doctor, there's one weird thing here regarding black holes, and that is the possibility that science, the laws of physics, don't prohibit, and I want to stress that, they don't prohibit things like negative mass. That's not to say it could ever be made or ever exists or is even possible, but in principle, you could have it, which changes the equation for black holes, because then you might be able to traverse one. Do you think this is a direction we will ever be able to go, or is it just pie in the sky?
Pie in the sky, I think. Negative mass is a really weird one, and I don't think it's anything we'll ever understand until particle physicists really get their head around the Higgs boson, which is the sort of communication particle that we think gives things mass. Perhaps there's another boson out there that gives things negative mass. Who knows? It's a bit of a weird one, because I think it's a really interesting idea, and it's a great thought, but it's definitely rooted on the blackboard at the minute. Let's put it that way. I think it could never be in our lifetime, for example, that we can ever do that. But the idea of negative mass and traversing a black hole is, that would be a cool sci-fi story anyway. I would read it.
I think it's going to be a sci-fi story for a very long time, if not permanently. I kind of look at it like the possibility of it sort of like driving a car at negative 10 kilometers per hour. No, you can drive in a different direction, reverse, forward, but you can't go negative, Yeah. And I kind of look at it like that there's just, maybe it's just one of those things that it's an interesting thought experiment, but you could never do it.
Yeah, thought experiment is a good way of putting that, I think.
Yeah,
for us anyway. Let's not say never, but thought experiment for now.
Speaking of things, never say never. In your book, you also go into the possibility that there is intelligent alien life in the universe. Mm-hmm. I'm a little bit pessimistic on this. I think it's maybe there, but it's pretty rare in both time and distance, and that intelligence is rare, but I think there are microbes everywhere. What's your sense of this? Do you think I'm being too pessimistic with that?
No, I don't think you're being too pessimistic. I don't want to give away the punchline in the book or whatever, but I think if you consider the scale of the universe and the sheer number of stars and the sheer number of galaxies that then have hundreds of billions of stars in them, it's difficult to say we're the only one planet in the universe that happens to have formed in the Goldilocks zone around its star and the Goldilocks zone in the galaxy, and, you know, a really sort of pretty quiet place in the universe that we've been able to thrive and we've been left alone for this long. But I think it's sort of one of those things where, you know, you can think about it all day, but it's a very different question asking, do aliens exist? Is not even intelligent life, does that exist elsewhere in the universe beyond Earth? And then asking, will we ever encounter aliens? And I'm very optimistic about the first, and I'm very pessimistic about the second. Optimistic about the first because, like I said, the scale, just when you start contemplating it, you can't help but sort of think about, well, we can't be the only one. And then pessimistic about the second because, like you say, the time and the distance between planets that will probably host intelligent life is so vast and so great that unless we encounter intelligent life with significantly more advanced technology than ours that can, you know, go at the light speed or whatever, all the sci-fi things of like warp speed and everything like that, then I don't think we'll ever encounter anything on Earth. And I don't think we will ever venture either beyond it to try and find other planets unless we significantly improve our technology.
Our technology, and we need to make sure we don't go extinct.
Well, exactly. Yeah, you know, we don't want to be driven off the planet in a sort of Wall-E scenario. Wall-E? I don't know how you guys pronounce that. I don't want to sound silly to Americans. Wall-E. Yeah, in that kind of a situation. And, you know, we don't want to go send a few adventurous types to go searching for intelligent life and have them bring back, you know, the mass extinction crew in a sort of Hitchhiker's Guide to the Galaxy kind of way. So I think we need to be very careful. I know Stephen Hawking talked about this a lot when he was alive, saying, you know, in any scenario that he could think of, we're not Chris Columbus, we're the Native Americans. So it's an interesting way of looking at it, a little bit of sort of maybe historical sort of like in that, but it's a difficult one to get your head around, like the scale and whether we will ever encounter aliens. I know there's people out there hoping we will one day. And there's studies out there that are actively listening as well, which is what I find really cool. You know, SETI is still always listening, and they've been investigating Voyager's star that you brought up before, that weird, oddly varying star that we still can't quite explain. And just actively listening for radio signals from space that could suggest that intelligent life is trying to communicate, or even looking for what they like to call biosignatures as well. So aspects around a star and a planet's atmosphere that would indicate that intelligent life is present there.
What's interesting about biosignatures is you don't really even need intelligence, which ups the ante, because then you can look for things like photosynthesis with the vegetative red edge and things like that. And then you can see a planet that it doesn't have the burden of intelligent life, which I think is probably rare by nature, but I think life, there's no real reason I can see that life itself would be rare. So I sort of expect the first detection of alien life will be some kind of biosignature.
Yeah, I hope so too. I think there's a lot of discussion about what the best biosignature would be. You know, people have suggested, well, methane, for example, would be a good biosignature. You know, for example, a lot of the methane in our atmosphere does come from cows, cow flatulence, if we're getting onto the topic.
And the oxygen as well.
Well, yeah, exactly. So the oxygen obviously produced by plants and everything. I think oxygen is definitely a good one because methane, for example, can be produced by volcanic processes and just geological processes in general. So it's really interesting to hear the astrobiologists, which is a great job title, discuss what could actually be the best thing to look for in atmospheres and planets. And I think another one that people tend to look for is ozone as well. Ozone's a really good indicator that life is present.
Well, and that also one of the chemical technosignatures is CFCs. You know, atmosphere destroying CFCs. And there's some people, Adam Frank wrote a book about this, that maybe the one commonality between all alien civilizations is climate change. And that, you know, even if you're highly advanced civilization terraforming a world, you're changing its climate. So it's kind of an interesting thing that's another signature. I mean, if you watched long enough and you saw an exoplanet go from uninhabitable to habitable over 100,000 years, good chance someone did that.
Yeah, exactly. Or even as well, like if you find a planet that is around a star that maybe you would estimate its effective temperature from its position, you know, its distance from its star and how hot the star is, and then you were able to get some temperature measurement from atmospheric conditions, and you found that they vastly disagreed, then you could say, well, perhaps there has been some sort of climate change on this planet that has been caused by, I hate to call them intelligent life if we're causing climate change, but yeah, intelligent life on that planet.
Now, I often wonder if the opposite of what Hawking said was true, that, he said we would probably be on the downside if we ever met an alien civilization. But then I wonder about things like gravity. If Earth's gravity well were just a little bit more aggressive and more massive, we wouldn't be able to escape it. So you wonder about these super Earths that might have an otherwise intelligent life that just can't leave their planet.
Yeah.
In which case, we got lucky with just the size of our planet.
Exactly, yeah. I mean, super Earths, obviously you're going to need eight times, like the one they just discovered, like a month ago, was 8 times the size of Earth. This one that had water in its atmosphere, it was in the habitable zone. You're going to need a much bigger rocket than we've been able to produce to get off the surface of that thing, even though it doesn't really have a surface because it's mostly a gas giant like Neptune. But say we did find something that did have like a rocky surface that was much bigger, it would be very difficult for that civilization to get off. But of course, that might then push forward their technology because they have a need for it to be pushed forward in order to get off the planet. And so that could actually accelerate their advancement in technology. The same way that sort of the space race in the 60s really advanced technology in the US and around the world because there was a need for something and they were pushing for a deadline and for a goal. And so that could obviously drive advancement even more. And perhaps you could turn your question on its head and say, well, if the Earth had been bigger, would our technology be more advanced by now?
That's something interesting. We were talking at the beginning about how sometimes things we don't know about, suddenly we find them and we realize the universe is quite a bit different than we thought. And a good example of that are super Earths. Because I remember the time back in the 90s before we really knew for sure there were other planets and our exoplanets existed. And now we find that one of the most common types are super Earths, which is something we don't even have an example of in our own solar system.
Yeah, it's really, really interesting. It's sort of the halfway point between like Earth and Neptune. Is what people like to think of it. So that's why sometimes they're called mini Neptunes and sometimes they're called super Earths. I think super Earths more so because it's a bit more attention grabbing and sort of media grabbing. But most of the time these super Earths are like actually quite gaseous. They won't really be rocky surfaced. And it is really interesting. And another example of things we don't have in our own solar system that we find everywhere else is hot Jupiters. So Jupiter-sized planets, gas giant, but it's like sort of at the distance of sort of Mercury or Venus from its star. It's incredibly close in the solar system. And the reason we think that this happens is that they do form out where Jupiter is in our solar system from the sort of, the really gaseous outer parts of a star's sort of where stars died and then a new star is forming. You obviously get all of the heavy materials sort of in towards the center where all the rocky planets form and you get a lot of the gases on the outside that the gas giants form from. But then what's happened is because they're so big, these gas giants that form, they then migrate inwards towards their star. They sort of go on a little wander and a journey inwards and actually end up orbiting a lot closer to their star than where they formed. Well, that raises the question, well, why didn't that happen in our own solar system? Why aren't Jupiter and Saturn, Uranus, Neptune, where Mercury, Venus, Earth, Mars are? And it's a good one to consider, and it's one that simulation people have been studying for a long time, trying to simulate the formation of the solar system. And I think they've realized that the reason that Jupiter is where it is because of Saturn, because Jupiter wanted to migrate inwards, but the pull of gravity from Saturn actually stopped it from doing so. And this comes back to the fact that we've got really lucky on Earth, because if that had happened, Jupiter on its way past Earth towards the sun would have been a huge disruption to the early Earth's formation and orbit. We could have ended up being either pulled into the sun, we could have ended up being pushed way out into the solar system, so either out of our habitable zone either way, or we even could have been flung out of the solar system entirely if we'd had a close enough pass with Jupiter in this gravitational interaction. So it's kind of another one of those things in the solar system that is a happy coincidence that we actually are able to be here as well.
I have just a shot in the dark thought. So our solar system's hot Jupiter failed, and it's a cold Jupiter. Mm-hmm. But when the sun swells into a red giant, will we then have a hot Jupiter, literally?
Yeah, probably. That's very true, because the red giant phase of the sun is estimated to completely engulf Earth. We're not entirely sure if it will quite reach Mars or not. if it does reach Mars, then Jupiter will be the closest planet to the sun. You'll have the asteroid belt and then you will have Jupiter. And so, yeah, the temperature on Jupiter will probably shoot up. And any intelligent life forms, perhaps trying to detect their own exoplanets, might end up seeing Jupiter as a hot Jupiter when they finally do.
Fascinating. Amazing. The solar system is just weird.
Yeah.
It's, as you said, there are just weird aspects of our solar system when, in comparison to other star systems that we can see, we're like, what is this place? Mm-hmm. But there's also another possibility that maybe we do have a super Earth and that it got ejected. Do you think there's anything to the Planet 9 hypothesis?
Mathematically and theoretically, yeah. I mean, there's a lot of evidence if you really look at the orbital structure and the orbital perturbations, so like the changes from what we expect them to be, that suggest that there probably could be a Planet 9 out there, perhaps beyond the orbit of Neptune, even beyond the Kuiper belt, that has been flung out on this huge eccentric orbit around the sun that we really want to search for. And so there's a continued effort to try and reconcile this sort of math that's telling us that something probably is there. This isn't just sort of like if someone's dreamed, oh, Pluto got demoted, let's try and find a bigger Planet 9. It's not come out of nowhere. It's definitely come out of the maths. And so there is this observational effort. So I know that, do you know about the Zooniverse, which is this online citizen science platform that gets people to classify scientific data? When scientists have far too much of it to look at themselves, you need the power of the crowd to get through it all. And one of the things they did was a search for Planet 9. And they did a really structured search for it, in the sense that they observed a very large section of the sky for over a couple of months, and then said, compare, is anything moving from this same patch of the sky from a while ago to now? And sort of a really, really specific way of doing it. And it was a really easy task for people to do as well, which I think was great. Obviously, you had to filter out asteroids and satellites and everything like that. But what that allowed them to do, and okay, fine, they didn't find anything, but that actually allowed them to rule out that whole area of sky, which is a pretty cool thing to do, to say, okay, if it exists, it's not there. It might be a negative result, but negative results are actually really, really
Sure.
useful in science, because it stops people doing the work again.
Fruitless work.
Which it was a good thing. So it's really cool that they managed to be able to do that. And it's also interesting to think, well, people might be saying, well, you could look in the whole sky for this thing. And yes, you could. We'd hope that Planet 9 would be on the ecliptic, this line where all sort of like the planets in the solar system will go across the sky, because the solar system is just a single plane of all the planets going around the sun in the same sort of plane. Pluto was tilted to that though, so maybe perhaps we're looking in the wrong place for Planet 9, and we should just explore the entire sky. But probably that sort of region around the ecliptic, 360 degrees around the sky, is the best place to start to look for Planet 9. And so what the Zooniverse volunteers did was at least rule out a section of that.
Actually, the Zooniverse is really cool. And in fact, one of the things that one of the ways that I ended up on YouTube actually was I was a planet hunter.
Nice.
During the time when Tabby Star was found, and I was sort of monitoring the forum over there and, wondering, what is this thing? Mm. And ultimately, the first video I posted on YouTube was on that star.
Nice.
Now, my last question for you.
Mm-hmm.
We were talking about archive and AstroPH papers, and there was a recent one that suggested Planet 9 might be a primordial black hole.
Yeah.
Do you think this is possible? And if so, the implications of that would be astonishing. But what's your feeling on that one?
I mean, there's nothing to say that we might have a small black hole orbiting around the sun. It's one of those things, again, that, like, nice idea. It probably fits the observations, decently. Like, there's nothing to say that it couldn't be a black hole. I think the odds of it being that are quite rare. But who's to say, primordial black holes that are formed, right in the early universe, that have sort of been left to their own devices as the universe and normal matter evolved around them. There's nothing to say that a primordial black hole wasn't in the vicinity of the sun as it was forming and happened to be trapped on this large orbit. But I think it's more likely that it's a captured asteroid or planet that's formed way out, or that, you know, one of these interstellar interlopers, they call them, like Oumuamua,
Yes.
that came to our solar system a couple of years ago. Like, I'd put my money on like that.
And now comet borisov.
Yeah.
But that in itself is interesting, because if it's a captured planet, a captured rogue planet, imagine what what that might be like, you know? I mean, it could be chemically significantly different than any planet in this solar system.
Exactly.
So who knows?
So that's why I mean, my money's on it, but I'm kind of hoping for that too, because I think we would learn more about our, you know, solar neighborhood and our sort of place in the Milky Way from something like a captured rogue planet or comet, whatever, than we would from it being a primordial black hole. Like you say, because it could have different chemistry, it could have a completely different makeup, you know, we don't know. And so that's what I'm kind of secretly hoping for.
One of the interesting things about comet borisov is that they did some preliminary, they took some preliminary spectra of it, and it actually isn't very different, at least surface composition, from a solar system comet, even though it has to be from somewhere else. So it's kind of really interesting.
It is really interesting, yeah. I think it shows that the solar neighborhood probably, and I'm talking like sort of, you know, the stars around the sun, which this comet probably has come from, probably formed from a cloud of gas that was probably very similar in composition of what we call metals, so anything heavier than hydrogen. And it doesn't really surprise me that if it's a nearby captured thing, that it might be quite similar. It'll
be interesting to see. And then, of course, we're bound to find ones that didn't form out of that cloud that have differences, and that it may be something, you know, maybe it's weirdly low in a certain element, like phosphorus, I think, that might actually be rare in some parts of the Milky Way. It's interesting times, because we can really study things at a depth that we've never been able to do before. And now with things like the LSST coming online, well, that's probably going to catch Planet 9 if it hasn't been found before then. So
exactly, yeah. So it's exciting times, and this idea of, you know, finding where in the Milky Way different molecules and different elements are more numerous or you know, than in somewhere else in the Milky Way is such a cool line of study. It reminds me of my old supervisor, Chris Lintop. He has this idea of a really habitable zone in a galaxy. So not just the zone in a galaxy where you know, don't have too much radiation from the black hole, and you don't have too much radiation from, you know, intergalactic space. You know, you're in the sort of happy medium in the middle, but also the part of the galaxy where you have the molecules so that you can make alcohol to make gin, and you have the molecules to make citric acid to have a lemon, and you have the molecules to make quinine to have tonic. And so the really habitable zone is the places in the Milky Way which have had enough stellar birth and death to give you the molecules to make a gin and tonic.
Amazing. And on that note, I'm going to go have a gin and tonic because we are out of time. Everybody check out Dr. Becky's YouTube channel, and also her book, Space, 10 Things You Should Know, 14 Billion Years for People Short on Time, which is available worldwide, but soon to be available in the US and Canada. Thanks, Doctor.
Thank you.
One of the great things about science are the seemingly endless mysteries that present themselves the more we learn. One unanswered question seems to always create 10 more new mysteries. I don't think this will end anytime soon. Indeed, I think it will only increase as instrumentation and study intensifies in the coming years. Buckle up, we're going for a ride. It's been so quiet around here lately, folks. I love it.
John!
What do you want? You have a virus.
John, just install the new firewall.
I will. There's like 14 floppy disks involved.
Just install the software.
Can I finish this pastry first? What? My pastry! YouTube is such hard work. On that note, we'll be joined next week by Dr. Abel Mendez for a discussion of exoplanet astronomy, astrobiology, and many other subjects, including the Arecibo Radio Telescope. See you then.